According to Muse manual, this algorithm can produce melodies that at 60 BPM last up to 13 years until they repeat themselves. Hello, that's Vlad is here, and today I want to talk about one of the most interesting music devices in my opinion, the Triadex Muse. It was built back in 1972 by Edward Fredkin and Marvin Minsky at MIT. And the word computer should be emphasized here because sonic possibilities of this device were limited to single square wave oscillator without any possibility for tonal change. Nevertheless, this device was really musical and could generate really interesting melodies. To produce and sell this device, creators started a company called Triadex, and the slogan of this company was "Computer for People." The idea was that it will even replace radio. So imagine coming home and instead of tuning into the radio station, turning on this device, putting some parameters there, and it starts generating some melody, which probably sounds not that strange nowadays after all this development of electronic music and ambient music, but looks like back in 70s this idea didn't take off. So less than 300 devices were produced and sold, which makes them extremely rare and highly collectible items. I don't remember when the first time I heard about Muse, but since then the idea of replicating it in software and combining with sonic possibilities of modern synthesizers popped up in my head over and over again. And eventually I gave up and decided to give it a go and started looking in internet for some information about the internal workings of the device. And luckily I came across brilliant emulation in JavaScript made by Donald Tillman. I highly recommend visiting his website. There you can play with this emulation and also read some information about Muse and also other devices. And yeah, so I thought that, okay, this emulation is done in JavaScript and Logic has scripter plugin that works with JavaScript, so probably I can somehow adapt it to work inside Logic. So I got kind permission from author to use this code and starting changing it and adapting to work within the plugin. And today I want to show you the results. So let's get straight to it. So I have an empty project with a single track containing software instrument. In this case it's Moog Model D with some bass selected, and now I'm going to play this instrument using Muse emulation. To do this I'm going to open scripter plugin. It's clean and empty. There are no controls here because nothing is defined in the script window. Couple of words about the plugin itself. So as you already know, it allows manipulating MIDI events using JavaScript, and it provides a relatively simple API. This API is pretty well documented on the Apple website. I will add the link to this page to the video description. In this case, we don't need to write anything from scratch. We just want to use existing script, and I'm just going to go and grab it. So the script resides on my GitHub page. This is living thing, so this script changes over time. I'm doing some bug fixes, improvements, sometimes add some new functionality there. So if you're interested, check from time to time this page. You can always see when the last time this script was updated. It says here, so it's currently 7 hours ago. So I will just open this Muse for Logic Pro X Scripter.js, and here's the script, actual script. I want to open a raw version of it. then it's just easier to copy and paste. So I just do Command A, Command C, and paste it here. And after that, I have to run it. So I do run script, and here we go. So all the controls are here. Script evaluated successfully, so we're ready to go. I'm not going to go too much into details of how this script works, so I'm just closing this window for now. Let's focus on the UI, and I would probably go straight to the core controls of the algorithm. We have these two sections here, so interval and sim. Well, Muse is a computer, and as majority of computers, it operates with ones and zeros. So how does it produce notes? It encodes the position of the note on the scale using a combination of ones and zeros. And it's assumed that the scale has eight notes, 8 positions, and so to encode these 8 positions, we need 3 bits. Yep, 3 ones or zeros. And the state of these 3 bits, whether they are 1 or 0, are controlled by these first 3 settings, A, B, C. D controls transposition to the 1 octave up. So when it's this bit, this fourth bit is 1, it will transpose the note up one octave. So how these controls work? They have really a lot of different settings. Actually, 40 of them, exactly as on the sliders on original hardware Muse. So let's see how those settings affect the behavior of those 1 and 0 bits. So if this control is in off, it means that it will produce 0. So, which means in this case, all the four bits, yeah, A, B, C, D, will be 0, which as a result gives 0. And these positions on the scale, they are 0 based. Yeah, so 0 means the root note of the scale. And in this case, the root note of the scale is C3. So if I hit play now, it's going to just play one note, which will be C3. Yeah, pretty boring. Now, next setting is on. This means that on this beat, on the first beat, it will be always 1. Yeah, so no matter what's happening, it will be always 1. So now we have the pattern here 1 0 0 0, which gives output 1, and on 0 based scale, this 1 is a second position, so it will be the second note. And currently here I have Ionian mode selected, which has the same structure as major scale. So in major scale, the second note will be D3. So with these 3 bits, we can encode 8 notes, and this fourth bit, as I promised, if it's on, it will just transpose the note 1 octave up. Now, this is all fine, but it's static. Now we want something changing. And then we enter this C region. So here we have several options from C half to C actually 8. They're not sequential. Let's start with C1. C1 setting means that on one clock bit it will be 1, on next clock bit it will be 0, and then it's going to just alternate between 1 and 0, which in our case means that it's going to alternate between D3 and C3. As you can see, this alternation happens on every quarter note. So this is the default resolution of the Muse sequencer, Muse clock. But we can speed it up to 1/8 if we select here C half. So C half means that half of the clock beat will be 1 and half will be 0. So if we do this, then it's twice faster. So the same way work all the rest of the controls in C region. So C2 means that 2 clock beats will be 0, 1, 2 clock beats will be 0, 1, 0, 1, 0, so 2 clocks, 2 clocks. The same C4, C8, C3, so the same principle. Using these C region settings, we can produce some melodies that will repeat all the time. Which is already pretty interesting. But we can go further with this. And to generate something really evolving, we need to go into this B region. And B region contains 31 different values. So what all those 31 positions mean? Muse has so-called shift register. So what is shift register? It's just a queue filled with ones and zeros, and on every clock beat it shifts, let's say, to the right, to one position, which means that the element on the last position goes away and some new element enters from the left side. And in Muse, this shift register has 31 positions, so exactly corresponding to the number of these options. And this setting, it actually says from which position on that shift register queue the value will be taken on the next beat. Yeah, so if we take, let's say, B10 here, it means that this first beat will be produced from 10th position of the shift register. Whatever passes through this 10th position, 0 or 1, it will affect the value of this beat. So values on this register, they shift one step to the right on every clock beat. And now we need to understand this new value which enters the shift register from the left side. Where does it come from? And this value is actually defined by these SIM controls. They have the same amount of options, so the same 40 options, and those options do more or less the same. What is different on this theme? It's what those values, what those settings actually affect. And here we have also like these 4 beats, and the rule is relatively simple. So if there are 0 or even number of ones here, so 0, 2 or 4 ones, the shift register will get 1 as an input on the next beat. If it's odd number, so 1 or 3 ones, then it will be 0. So this way the contents of the shift register always changes. And what is even more interesting is that here we can also set these drop downs to read values from the same shift register, and it creates like a feedback loop. So these settings, they affect what will go inside the shift register, and shift register affects the settings themselves. And this can produce really long evolving melodies that will repeat itself after a really significant amount of time. According to Muse manual, this algorithm can produce melodies that at 60 BPM last up to 13 years until they repeat themselves. And what is interesting that this algorithm is 100% deterministic, meaning that knowing the original settings, you can predict which note will be played at any point of time in the future. It still may seem a little bit random because it's sometimes hard to trace all the factors that affect particular event, which is somehow even philosophical statement to some extent. So that's the basic workings of the algorithm. There is an official manual of the Muse still available online. I will drop a link to this manual to video description, so you can go through all the stuff in more details. So let's go through the remaining controls here. So the speech control, as I said, is a root node of the scale, and here you can go from G1 to C5. And mode is actually modes. Yeah, so here I defined several of them. You can add more. This is probably one of the rare cases when you want to go in and change the script itself. Let me quickly show how to do this. So if I open script editor, here those modes are defined, and they defined in terms of semitones. Yeah, so Ionian, let's say Ionian mode, which is the same as a major scale. We have two semitones is a tone. Yeah, so tone, tone, half tone, 3 times tone, half tone, so major scale. Yeah, and there are exactly eight position here. So this is this 8 position encoded by this first settings ABC. So if I want to add a new mode here, I just copy it to the next line and call it, let's say, my mode. This green is actually just the comments. It doesn't affect how the script works. So make sure that this comma is not missing after you copy that, otherwise it won't compile. So this is one thing. And then if we go a little bit down, there are mode names here. So here we need also to add, let's say, my mode. And once we did this change, we do a run script, and here we go. So this mode is here. The next setting is velocity, which is just MIDI velocity from 0 to 127. Rest is something Muse specific, so when it's set to normal, on every clock beat, algorithm will produce the note. If rest is selected, then it can skip some notes. Reset is actually doesn't reset the UI of the plugin, but it does reset internal state. So this shift register gets cleaned, and the melody will start from the beginning. So channel is just a MIDI channel, so it's up to 16, and I can have multiple instances of scripter, and each can be set to send the notes to a particular channel. So it's pretty convenient if you work with multi-timbral instrument. Important thing here to remember is that this setting like on this on the channel should be all. Otherwise, if here I will select some particular channels, then no matter what this setting says, every node will be routed to this one. So here we need all if we want to use multiple instances with different channels. And the next one is roll the dice. I added it just for fun, so it just randomly changes the settings on interval and theme. So that's it regarding the melody generation. And one more thing that I added just recently to this script is actually rhythm. So as you noticed already, by default Muse generates straight rhythm. But in many cases I want something more dynamic. So I added Christopher rhythms here. So Christopher rhythm, the idea is basically the same as Euclidean rhythms. So given the number of positions and the number of onsets, it distribute those onsets as even as possible across these positions. If I select Christoffel, the resolution of the sequencer changes to 16 node. So we have then 16 positions, and this number of onsets will be distributed evenly as possible across the across this region. Which is a little bit more interesting. So that's it about the script itself. One more thing that I want to mention is how to record the output of this script to the track, because sometimes you want just to let it generate something and then change some notes so it fits better into the track. So it's one of the recent additions to the logic. So to record MIDI fix output to the track, I will go here, and this area below the plugin is highlighted. If I click it, there is option here, record MIDI to track here, and it shows these two orange triangles or arrows. And what does it mean is that everything above those arrows will be recorded, and everything below will be skipped. So now if I hit record, captures all the output, and now I can modify those notes and do some additional changes to the result. That's it for today. I'll be really happy to hear your feedback. So if you have time, please drop me a comment. And thanks for listening. See you next time.